Sorry, is it my screen visible?
Yes, your
Yes, sir.
skin is visible. Please make it full screen. Side. Side.
Okay. Good afternoon, everyone. Uh,
It is full screen now. Okay, good.
Okay. My name is Jayadev Meher. It's supervised in NIT Rourkela under the supervision of Krishna Roy and Arnab Ghosh. Yes, I'm here. I'm here to demonstrate how to integrate multiple renewable sources to a common DC link. This is the title. Before that, I like to give some brief overview of the experimental setup. It will be helpful to understand clearly. This will be the content of our session. Why we need to integrate the multiple sources? This should we should understand this. First, the few points is the I'm displaying few points. Why we need to integrate that one? Uh, like resource diversification. It means combining different renewable resources reduce the dependency on a single source. Like if you are installing only PV in your router, whenever the sun is it depend on the only one source. If you integrate more than one, then if the sunny some of the every day is not the sunny days in winter season before, in that time will it will be reliable to integrate more than one source. Like other point like grid stability, more than one source it will uh, integrating more than one source, it will be diverse energy source can complement each other like solar and PV. For example, we can generate in the daytime only, whereas the wind, most of the maximum energy can be extracted at the night time because of its high airflow. In that case, we can say integrating both, it will be reliable compared to single one. And reliability and resilience, mixing more than one sources can be, it will be helpful to withstand in the fluctuation in the um, energy generation and like outrage or weather condition, severe weather condition or some other disturbance. If one source is unable to deliver power, we can get from the other, or half of the source is giving, half of the power is giving from one source and half from the other source also. That way we can be very much reliable. It, and it gives also environmental benefit also by reducing the uh, emission of harmful gases, like will be less dependent on fossil fuel. That these are the few points. Then this is the overall block diagram, which is I will give a experimental demonstration on this. In this case, um, we are using PV panel, Pico-hydro and battery as a input source, and it will be integrated to the DC link through specific converter. Like PV will be integrated to this DC link through the specific converter. Uh, Pico-hydro will be integrated to DC link using diode bridge rectifier fed buck converter. The battery we are integrating to eliminate the fluctuation or variation in the DC link voltage, or to stabilize the DC link voltage, we are using battery through a DAV converter. Let's understand why we choose the specific converter to integrate all these things. Like why we choose the specific converter. Compared to the buck boost converter, simple buck boost converter, it can handle wide range of input voltage, which is a very ideal condition for the solar. As the irradiation changes, the solar output also changes. It will be that can handle that variation can be easily handled by a circuit converter, and it can step up or step down according to our requirement or the generation. And it can track also efficiently track maximum power It helps to extract maximum power from the PV panels so that we use the safety converter. Here you can see in experimental setup, we use a safety converter having inductance value is 1 millihenry and the capacitance input and coupling capacitance as 470 microfarad to 50 volt. And the MOSFET we are using for 47N60C3. To understand about the MOSFET, I've given VDS. That is the we. If you see the MOSFET data sheet, we will find the VDS will be 650. It can withstand up to the 650 volt, and the current that can be conduct maximum current it can handle up to 47 amp. All these converter which we are fabricating, this is only for the high power application. Okay, then DAV. Why DAV converter? We are choosing compared to the buck boost converter. We can choose buck boost converter as a bidirectional buck boost, but we are choosing the DAV converter because it can give a additional benefit of soft switching. Whenever you are going to use this system for a high power, you need to be the switching and high frequency. You need you need to eliminate the switching loss. The switching loss will be high, so that you need to eliminate that one. For that, you will use the switching, soft switching, which will eliminate the switching loss. And it can handle a wide range of input and input output voltage with high efficiency. Some of the literature already they prove it that using DAV converter, the charging and discharging also, it can give up to 98% efficiency. And also it provide the isolation between the DC link and the battery, which is the bidirectional boost converter unable to provide the isolation. Okay, and bidirectional power flow also the inherent characteristic by shifting the phase shift between the primary and secondary bridges voltage, we can control the power flow between the primary and secondary. Here, the in figure 4, also a single phase shift modulation switching for a DAV converter. Here in the upper figure, we see a phase shift of about alpha degree. VP is the primary and VS is the secondary voltage. If VP is leading to VS, means the secondary voltage. Primary voltage is leading compared to the secondary voltage. It means the whatever the power you are giving at primary side, it will be transferred to the secondary side. And second case, then the reverse. We change the alpha. If the alpha in above case, consider the alpha is positive, and in down figure, second figure, we'll say alpha is negative, means V is secondary. We okay. Oh, there is uh, some mistake is there. You can see. Let forget the figure. If alpha is a negative, if primary is lagging compared to the secondary one, then power will be transferred from the secondary to primary. In bottom, we see we are using a battery capacity of 42 ampere hour at 12 volt output nominal voltage, and a DAV converter having the inductance which is available to the as a module stack for 14 milliampere, and having a transformer with the leakage inductance combined with the transformer, which has turned the CO of 300 is to 40. Coming to the diode bridge rectifier fed buck converter, the Pico-hydro generator, which are we are integrating, it's generating a three phase power at 415 voltage, line voltage, which is then rectified through the diode, three-phase diode with rectifier. Then that rectifier voltage is stepped down to a DC link voltage by through this buck converter, which both two are, we can see both two are integrated, I mean combinedly, and whatever the output we are getting here, we can easily regulate through the buck converter. Why you choose this one? Because because of this is a simple, very simple design, low cost and easy to operate also. And we consider the other converter, this is a compact in size. Okay. Then to regulate this buck converter, circuit converter, DAV converter, the switch has to be regulated. Uh, for that, you are using microcontroller. Some of the microcontrollers. One is a C2000 TMS 320 F28379D. The figure 6 shows the overall picture of the microcontroller, and the right side it's shown the uh, pin configuration. Don't worry about this microcontroller. There is a special session for this one. You will understand. We will get it how to generate the pulse and how to control, or uh, im- how to connect with the MATLAB and generate the pulses. You can. There is a special session for that. I'm not going on depth. Only give you the information about the pin and which pin you are using for the PWM output. For the DAV converter, there will be, see, DAV converter to regulate this one, the S1 and S3 has to switch at a alternatively. Means if you for 50% duty cycle, switch one is on, means next 50% S3 will be on, and S1 S4 are both are combinedly on, and complementary to that S2 and S3 has to on. So you will see we need, if we operate the DAV converter, we need four pulses, S1 S4 1, which complementary to that one, S2 S3, and for secondary bridge S5 S8, which will be phase shifted from the S1 S4, and complementary to that S6 and S7 we are giving. For that, we are using pin 40, 39, 38, and 37 as the PWM output pin, and 80, pin 80 is used for the septic converter. For controller you are using Arduino Uno. Most of you are already familiar with this, I think. Um, you are using pin 9 as a output, as output PWM signal at 20 kilohertz frequency. Uh, Table 1 shows the experimental parameter value which are in use. While using SEPIC converter, you are giving input around 21.42 voltage, and we maintain a DC link voltage 40 volt, around, sorry, 50 volt. Only 50 volt you are maintaining. For that, SEPIC converter output has to be 50 volt. Buck converter output has to be 50 volt. DAV converter has to be, output has to be 50 volt. Okay. This result will be observed in the experiment. Okay, this is the a figure of overall experimental setup. So we'll go live video how to integrate. I'll dictate how to integrate the uh, all these sources to a DC link voltage.
Mr. Jayadev, please unmute it.
Sir, camera is visible, right?
Yeah, it's visible.
It's visible, right? Am I audible, sir?
Yes, you are
Yes,
audible. Please
yes,
discuss.
yes. Audible and visible.
Okay, okay, sir. Bring that camera to closer. I'll show you. Uh, this is the safety converter. You are using MOSFET for this two inductor and capacitor, which is around 470 microfarad, 440 volt. We are giving pulse through the C2000 microcontroller. This will given to the uh, it is going to the driver circuit. Why need the driver circuit? From the microcontroller, whatever the pulse we will get, only 3.3 volt. But to trigger the MOSFET, we need 15 volt, around 12 to 18 volt, so that to shift that signal up to the 15 volt, we are using a MOSFET driver circuit. All this circuit, whatever you are looking at, this is made only on this uh, this lab only, designed and fabricated in this lab only. This is the driver circuit. Uh, there is session on this driver circuit and power circuit also. Don't worry about that. You will learn how to design and fabricate also. This is the power circuit. Driver circuit need 15 voltage DC supply to shift that 3.3 voltage pulse to a 15 volt. That's why we are designing a isolated power supply, 15 volt DC power supply. Uh, this transformer help to isolate from both terminal. we'll we'll what do we do? We'll maintain the SEPIC output voltage to a 50 volt. Then from the buck converter, this is a three-phase diode rectifier followed by a buck converter. This is a buck converter. All these are designed here only, here and fabricate also this lab only. Um, from this buck converter, we'll maintain the 50 volt. Then from the DAV battery side, we'll maintain the same 50 volt, and then we'll integrate. First, we'll maintain this the peak converter voltage into 50 volt. Okay, for that, uh, this time solar is not available. That's why we are using a DC power supply to make the DC link voltage. Okay, switching on. This is the load box, three-phase load box. Individually, you can use per phase into a three independent load also. This load will be integrated to the that buck converter. Before integration, when we are making the DC link voltage to 50 volt, first of all, we have to connect a different load in the output converter, because SEPIC converter cannot be operated at open circuit. Similarly, buck converter also cannot be operated at open circuit. We have to connect some load to make that voltage. After voltage is maintained at DC link voltage, then will be integrate from this crossover switch, DPST and DPDT switch. Will integrate all these three. Then we intentionally remove the load, some of the load, whatever the which is our requirement. Okay. First, we need to switch on this. This is a power supply. If you see the pulse here, we are getting at from sales to drone. This is 70%. You can see that clearly. Okay, 70%. Then what we do? We make the output voltage 70. See, you can see it's around 50 volt. The output from the circuit converter is around 50 volt. $49.2 something. Okay, it will be okay. Then first converter making 50 volt, then we will switch on the DAV and we'll make the 50 volt. Please turn on that switch. Before that, I'll show you the pulse. This see the DAV converter. This one is boost side, high voltage side. This one is low voltage side. Means low voltage side is connected through low voltage side is connected to the low voltage battery, and the high voltage side will be connected in the DC link. Okay, we'll see the from primary. This is your 50% duty cycle, and next is alternating to that one. You can see here. Okay, let me take this one. And the other one is will be and very difficult to pull this one. Okay, this is alternating to first leg. You can see ground is not connected, that's why its noise is coming. We'll turn on the DAV. Before that, we'll measure the voltage from input and output side. Okay, for that we are using a differential probe. You can see the voltage is around 54. You can change this resistance value and make it to 50. Okay, it's around 50. We'll check the peak converter output. This is 31. So we'll increase the voltage, input voltage, to make it 50. Okay, these are 50. Both the voltage are 50. So now we can integrate these two. Right? Okay. Then next is the Pico-hydro. You can see down, you can see this is the synchronous machine and a induction machine coupled one will give mechan mechanical supply. We are rotating the synchronous machine shaft up to 1500 through the induction machine. We are giving supply to the induction machine so that it will rotate the synchronous machine into 1500 and it will operate at a 50 hertz and it gives 450 volt at uh, rated rated excitation. Whether we need to turn on the machine. Before that, turning on, after running the machine, this will be get very noisy. Very difficult to say something or understand anything. So you just observe. I will turn on the machine and I will maintain this voltage up to 50. Then we first these two integrate means the peak, sorry, PV, then battery. First, these two will integrate. Uh, by turning on this switch, this will be in parallel. Then this connection, you observe the connection. These two connected connection given to this one, this terminal. If when I want to connect this into this system, then I have to connect this one. After connecting these two switch, all three are become the parallel, and the DC link voltage will be maintained at a constant value. Just observe. Okay, you can see this is around 50 volt. 50 volt. Now it's time to integrate all these things. First, we will integrate these two PV and battery. See, and the voltage will maintain at 49.8 ampere. Then we will integrate with the Pico-hydro. See, the voltage is 46. Means because of the resistance value, yeah. After connecting, we can remove some of the resistance. But I am not removing any resistance because after, when I have to disconnect, the resistance should be connected at the output. Otherwise, the buck converter and SEPI converter, there is chance of capacitor loss. Here you can see here this. This is the output input output voltage from battery and here. And one more thing, you can measure inductor current here also. Some clamp meter you can measure here how the inductor current is working on that. Using this one. See, you can see the inductor current, the variation. Whatever is the way study in the theory, it's following the same shape. This is because of the noise, and we are not using some snubber circuit. Because of that, this are giving some noises. Overall, it's coming fine. So this is how you will integrate. Before removing that, first I need to maintain some value and some. Let me show you the output current. You can see here the current is around 4.6 m. 4.6 m. Positive means its discharging current is 4.6 m. And while coming measuring at the output side, we'll find this one. It's around 0.7. It's delivering 0.7 to the load from battery side. From the PV side, if you see, it's giving 0.3 ampere. We are using very high resistance. That's why here these two are very less. The current are very less. Although the DC link voltage is only 50 volt and the resistance is value around 200. That's why it's coming very less. And you see the current is providing 0.4 from this is generator side, Pico-hydro generator side. Okay, the voltage is around it's running under 500. Till now the voltage is maintained at 56. Okay, then we have to remove one by one. First, I will disconnect the machine. Okay, then I will disconnect this PV with source. Let's see. I make the excitation 0. And stop the machine. Okay, now all our system are isolated. See, this waveform is coming only when DAV is running with the battery only. When all three are connected, some noise are coming because of the rotating machine involved. Some noise are coming. So when you use some filter, this will be you can eliminate from using some filter. Okay. Mr. Martin.
Hello, video is not, we're not able to see the video.
Okay, sir, I'm working with it, sir.
Okay.
Working sometime. That's all. Okay, sir, let me rejoin. I'm not able to share my screen. I think there might be some issue in. Okay, I'm good. I got it.
Sir, the session is over, sir. Hello.
Sir, I'm not able to share my screen. Um, I think some network issue, I think. Not able to share it. That's all from my side. Coming to the conclusion, we are successfully integrate these three sources: PB, Pico-hydro, and
Video is not visible.
uh, okay, let me check. It's visual, right?
Yes, it is now visible, sir.
Yeah. Uh, Coming to the conclusion, we are successfully integrate all the three sources: PB, Pico-hydro, and battery using the specific converter for all of them. It we can conclude from here, right? It giving a flexibility and scalability of modern system for high power application. We are using now we are testing at low power around 50 volt DC link, but we are planning to go up to 220 DC link voltage and overall system will be around 5 kilowatt. We are planning on that and working on this. And this is only for the open loop demonstration. And we are working on the closed loop also with advanced controller and some in future you are planning to implement some AI ML technique also. And we'll go to the more sources, not up to the three, and we'll use more than three sources only. Um, okay, that's it. These are the references. I have followed some of them. If that's all from my side. If you have any query or something, then please.
Good afternoon, sir. I am Krishnakant Gautam from Gwalior. Can you please show
Uh,
the previous slide where the references were mentioned? I would like to take a screenshot if you permit.
this is only for few only. I have followed around 34 or 50. I thought the screen slide will be more. That's why I only put only first five only. If you want, I'll tell you, sir, that he will share the references, or
Yes, sir, that
that will be
will be
okay.
fine.
Sir.
If you can share your references, it will be of great help for us.
Okay, so no problems.
Thank you.
Any more queries?